This is part 3 of the lecture on the law of inertia. In the second portion of the lecture, at the conclusion of the lecture, I performed a demonstration involving water inside of a coffee can. As I was performing that demonstration, you may have thought to yourself of a similar situation that I'm sure that a number of you are familiar with. And that's what happens when you ride a roller coaster. So, similarly to the water inside of the coffee can, with the water safely staying inside of the coffee can, you yourself have experienced this before if you've ever ridden a roller coaster that has an upside-down loop. So here's an upside-down loop like so for the coaster. Let's say that the coaster cart is here, and here you are as a passenger inside of the coaster. Let's say at this moment that you're moving in this direction like so. Once again, think of the vector that I've drawn here as a representation of your inertia. So this is the passenger's inertia. Okay, and then as the coaster cart traverses the upside-down loop, there is a force exerted upon the coaster cart, causing it to turn. Is that force exerted upon the person? No. So then therefore, because the person has inertia, a tendency to remain in motion like so, that person will do so until a force is exerted upon that person. So the combination of the passenger's inertia and the fact that the force is exerted upon the coaster cart, not the person, well, that then safely keeps the passenger inside the coaster cart and above a certain minimum speed. It's perfectly safe to actually traverse the loop without any restraints whatsoever. Now, of course, you're never going to get on a roller coaster where they allow you to take the restraints off. The restraints are always locked on roller coasters before the roller coaster trains even leave the station. But above a certain minimum safe speed, conceivably, you actually could traverse the upside-down loop and still stay safely within your seats. Now, another example that is similar to this involving a roller coaster involves, for example, going over a hill. A perfect example of what I'm about to describe is actually the ride Goliath at Six Flags Magic Mountain. For those of you that are familiar with that roller coaster, there's a portion of that ride where you go over a short, sharp hill. And then as you do, you may feel yourself rise out of your seat a little bit and then come back down. What's actually happening is for a brief moment as you crest the hill, you are actually a projectile. The following is happening. All right, so let's say, for example, that right here is a coaster hill, like so. Okay, and then here's the coaster cart with a passenger inside. And let's say that this is just a moment before you encounter the crest of the hill. So you're moving in this direction at this moment. Once again, think of this vector here as a representation of the passenger's inertia. Okay, now as the coaster cart traverses the hill, the coaster cart, by the way, itself is actually not just resting on the tracks like an ordinary passenger train or something like that. Instead, the next time that you ride a roller coaster, take a look at the wheel assembly of the roller coaster. You're going to see that it actually wraps around the track like so, and this then holds the coaster train to the track. So the coaster train itself is not resting on the track as it would be like a normal passenger train. So then therefore, to make a long story short, as the coaster cart then goes over the hill, there's a force that's exerted upon the coaster cart, causing it to then traverse the hill. That force is not exerted upon you. So then, therefore, if you go over the coaster hill fast enough and you don't have any restraints, then the following is going to happen to you. Like so. And then you become a projectile, which is obviously what you don't want to have happen to you, of course, when you are riding a coaster train. So for those of you that are familiar with the ride Goliath, and there's that portion of the ride where you go over that short, sharp hill, well, for that moment, the ride is engineered precisely such that you do, in fact, become a projectile for a brief moment of time, just maybe a few tenths of a second or so, as you traverse that hill. Okay, now a situation or a scenario that is very similar to this is something referred to as the vomit comet. Okay, the vomit comet is not a name that's given to a roller coaster. Instead, it's a nickname. It's a nickname for a plane that is specifically used by NASA to simulate weightlessness conditions when they are training astronauts. Have you ever seen file footage, for example, of the astronauts inside of this plane and they're weightless and they appear to be floating around the cabin? That's what I'm referring to here. Well, that passenger plane basically is an ordinary passenger jet, just with all of the seats taken out. They, I believe, use a Boeing 727, which is an old passenger jet. Well, that particular passenger jet, it just operates at an altitude which is very similar as that of an ordinary passenger jet, 35,000 feet or so above the ground. Now, the Earth's gravity, 35,000 feet above our heads, is basically the same as it is here at the surface of the Earth. So then, therefore, if gravity is the same inside of that plane, how is it possible for the passengers inside that plane to be weightless? They're not. They're actually instead in free fall. The following is happening. So let's say that right here is the plane itself, like so, and here's a passenger inside the plane. So what the pilot does is he makes sure that the plane then climbs at a steep angle, like so. And then the pilot will nose the plane over. When the pilot noses the plane over, a force is exerted upon the plane, causing it to turn over like so. It's like going over a hill, for example, on a roller coaster. Is that force exerted upon the passenger? No. So then therefore, if the pilot is skilled enough, what he's actually tracing out here, the path associated with this plane, is a parabola. And then therefore, the plane and the passengers inside actually then end up in free fall. So right here, for example, is the plane on the other side of the vertex of the parabola, like so. And then the plane and the passengers inside are in free fall. Both are accelerating downwards at 9.8 meters per second squared. Passengers in free fall. So the word weightlessness is somewhat of a misnomer, because in this case, no, the people are actually not weightless. Instead, what's happening is that the people inside the plane are in free fall. Now, of course, this condition cannot persist for a long period of time, because if it did, then the plane would just smack into the ground. So usually what happens is after maybe about 30 seconds or so at the most, usually what the pilot will do is the pilot will nose the plane back up again like this. A force is exerted upon the plane that causes that. And then, of course, everybody falls to the ground inside of the plane. That's why inside of that plane, if you've ever seen file footage of it, you'll notice that basically the entire interior of the plane is lined with padding. So ultimately, the passengers inside the plane are in free fall as this situation occurs. How many of you have ever seen the film Apollo 13? It was directed by Ron Howard in the late 1990s. It very closely and in a very detailed manner goes through exactly what happens with a specific Apollo mission in the late 1960s and into the early 1970s. Well, during that mission, there was an accident. The accident is depicted very well, and the actors then portray the astronauts and what happened during that mission. If you've not seen that film, watch that film. The film, by the way, the entire theme of the film is problem solving. But regardless, however, you will see various scenes inside of the film, or in the film rather, where the actors appear to be weightless. While they're actually in free fall, how they actually did those scenes is not a special effect. Instead, what they did was they built the set for that movie inside of the Comet. And then therefore, every time that they nose the plane over like so, such that the plane ends up in free fall, that's then when they filmed those scenes. If you watch those scenes, however, very carefully, you'll notice that the actors are only in free fall for brief moments, maybe 15, 20 seconds or so at a time, before the camera then cuts away to another angle. In other words, what they did was they filmed all of those scenes in 20-second increments or so while they were in free fall, and then they edited it all very carefully together to make it look like that the actors are in free fall conditions continuously throughout those portions of the film. But they actually built the set for that movie inside of the Comet. There have been a few other movies since that have done the same thing. Okay, now next, we're going to do a little bit of erasing here. Getting back to roller coasters for just a moment, by the way, there's actually a roller coaster that gives you about 6 seconds of free fall at Magic Mountain. Okay, think carefully about what roller coaster I'm describing. The roller coaster is Superman. Okay, if you're not familiar with the ride Superman at Magic Mountain, it's probably one of the best roller coasters that's there. The entire ride only takes about 30 seconds or so. But here's basically what happens during this ride. Okay, here is how the coaster track is shaped. and then you have the coaster cart like so, and a passenger here that begins at rest at the beginning of the ride. And then by means of something called an electromagnetic railgun, you inside of the cart are accelerated out of the station. You ultimately reach a top speed very quickly of over 100 miles per hour. But then after that, basically you coast. You coast up this vertical tower like so, and then come back down like so. And then the same electromagnetic railgun that accelerated you in the first place, this then slows you down at the end of the ride, and you ultimately end up at rest here once again inside of the station. The entire ride literally takes something like 25 or 30 seconds. However, when you're near the top of the tower itself, by the way, is 40 stories tall. When you're near the top of the tower, for about 5 or 6 seconds, you are actually in free fall conditions where you're actually accelerating downwards at 9.8 meters per second squared. Have you ever tried to do the following, for those of you that have ever ridden that ride? Have you ever taken a small object with you, for example, and then at just the right moment you let go of the object while you're on the ride, and then the object itself appears to float above your hand? Well, is that what's really happening? No. Instead, what's really happening is that both you and the object are accelerating downwards at 9.8 meters per second squared. You're actually both in free fall. So, to illustrate, let's say that right here is the coaster cart near the top of the tower. And then you've got this little object like so, like a tennis ball, for example. Both you and the tennis ball are actually accelerating downwards at 9.8 meters per second squared. If you're having trouble visualizing this, let me show you a very simple demonstration of this idea. In order for me to do so, however, I'm going to have to move the phone a little bit, so bear with me. And I'm going to try to do this without dropping my phone. There we go. Actually, let me tilt it a little bit further. Once again, bear with me while I do. Okay, there we go. Okay, and then I have an object here like so, this paper clip. And now what I'm going to do is mimic the best way to see the free fall conditions on the ride Superman. What you actually want to do is take the small object and then let go of it above your hand just before you reach the very top of the ride. And then the following happens. Watch carefully. Like so. After I let go of the object, from my hand's point of view, it looked like the paperclip was floating above my hand, but that's not the case. Both my hand and the paperclip were accelerating downwards at 9.8 meters per second squared. Both my hand and the paperclip were in free fall. That's what's happening on the ride Superman during these couple of seconds near the middle of the ride. Okay, let me move my phone back. And then let me tilt it again, like so. Okay, let me do a little bit of erasing. Okay, my next conceptual example here is extremely important. This example was actually first written up by Isaac Newton himself in his book that he wrote in the late 17th century. I'll get to that and those details at a much later date. However, for now, it is this next conceptual example that allows you to make the leap between understanding that motion near the surface of the earth and motion in the heavens are actually the same thing. It has to do with what is called an orbit. Okay, let's say that right here is the Earth like so. And now to begin this description, let's then take a look at the following scenario. Let's say that we have astronauts, for example, inside the space station. The space station orbits the Earth at an altitude of just over 200 miles above the ground. Now that sounds like a lot, but the Earth's gravity 200 miles above our heads is basically the same as it is here at the surface of the Earth. But then you look at the astronauts inside the space station, if you've ever seen video footage of them, and you will see that they're in weightlessness conditions. How can that be? That is, how can the astronauts be weightless if the Earth's gravity 200 miles above our heads is basically the same as it is here at the surface of the Earth? It's because they're not weightless. Instead, they are in free fall. The following is happening. When an object is launched into orbit, it is not launched straight up like so. because if it was, then the object would just instead fall straight down again. Instead, the object is launched as a projectile on an angle. Let's say that you launch the projectile with a relatively small amount of speed, say like so. Well, then the projectile is going to travel some distance and then fall to the ground. Let's say now you launch it at a greater speed. Well, it's going to then travel a greater distance like so, but then eventually fall to the ground. Notice what's happening on this diagram. Imagine, for example, launching the projectile such that horizontally it has enough speed such that as it falls, the Earth's surface curves away from it, like so. And then the object ends up in free fall around the Earth forever. The object ends up in orbit. So for example, let's say right here is the space station, and then right here is a passenger inside. Both the space station and the passenger inside are in weightlessness conditions. They're actually in free fall. The whole time they are under an acceleration due to gravity towards the center of the Earth, but they have enough horizontal velocity such that as they fall continuously around the Earth because the Earth's surface curves away from them as they do. So it is with this conceptual example, we now begin to make the leap, if you will, in understanding that motion near the surface of the Earth and motion in the heavens, if you will, are actually the same thing. Let me go ahead and conclude this portion of this lecture with this scenario.